Hello, my name is Jules Bates, and this summer I researched in the Human Neuromechanics Laboratory under the direction of Dr. Daniel Ferris on a project involving virtual object tracking using electromyography. I would like to take a second and tell you a little bit about myself. My hometown is Pace, Florida, and I currently attend the University of Alabama where I'm studying chemical engineering. I'm also getting a minor through the Randall Research Scholars Program, and I anticipate graduating May of 2023. In our normal lives, we rarely consider the obstacles we face, whether it be maneuvering through a tight crowd or making a split-second decision to leap over a puddle of water. These obstacles and sudden changes in terrain can cause problems for people who use prostheses. While there have been many innovations over the years, many powered prostheses lack the ability to adapt to unpredictable environments. There are different methods of control for powered prostheses. A state-based control uses predetermined states, such as opening and closing a hand or flexing and relaxing a foot, but there is no direct control over the magnitude of torque. Myoelectric control uses the subject's muscle activation to control joint torque. With state-based control, subjects are limited to the predetermined movements and they are not directly in control of the prosthesis apart from the physical attachment. With myoelectric control, the subject has direct control of the prosthesis. Electromyography, or EMG, is used to record muscle activity so the user can signal when to move the prosthesis, with torque magnitude being relative to the magnitude of the signal. A previous paper discussed motor control and learning with lower limb myoelectric control using one muscle to control a virtual object. For my project, I investigated myoelectric control of two antagonistic muscles, or a muscle pair where one muscle contracts as the other muscle lengthens. The previous paper only used the tibialis anterior, or TA, which is a muscle next to the shin. In my trials, both the TA and gastrocnemius, or gastroc, which is the main calf muscle, were used to control a virtual object. The movements of the virtual object were controlled by dorsiflexion and plantarflexion, which is the flexing up and down of the foot respectively. The TA activates during dorsiflexion, and the gastroc activates during plantarflexion. Electrodes were placed parallel on both muscles to record EMG signals. My setup was geared towards testing non-disabled subjects, but the main goal is to have subjects with residual limbs perform the learning tasks to compare with the non-disabled subjects. To perform virtual object tracking, electrodes were attached to the TA and gastroc along with a ground electrode on the ankle. A co-opt EMG system was used to stream EMG data to a Raspberry Pi, which sent normalized EMG data to a computer. This data was displayed in real time, so there was direct control over the movements of the virtual object. Dorsiflexion moved the object upward, while plantarflexion moved the object downward. A target was displayed on the screen for 20 seconds while the subject moved another object in an attempt to match the target movement. The results of this project will show a comparison between the initial attempt and the 20th attempt of virtual object tracking using EMG signals. The left graph shows a full display of all 20 seconds of the tracking attempt that was seen in real time on the computer monitor. The EMG data has been high-pass filtered, rectified, and low-pass filtered to generate a smoothed EMG signal. The right graph shows what the real low-pass EMG looks like during a tracking trial. Before there is upward movement of the virtual object, the TA is activated, and before there is downward movement, the gastroc is activated. In the first trial, there's little control over the virtual object and the EMG signals look sporadic, but by the 20th trial, the EMG signals are consistent and there's a big improvement in the control of the virtual object. Along with dynamic trials, static trials were also performed to see how well the object could be stabilized. The error was calculated after 5 seconds. The first static trial is similar to the first dynamic trial where the EMG signal is difficult to control and the virtual object is overcorrected when trying to match the target. By trial 20, the object is easier to control and the EMG signals are consistent. When comparing an intact subject with a previous paper on intact versus amputee subjects, it can be seen that the results are very similar even when using two muscles instead of one. More data would be needed to state a definitive conclusion, but it is possible that learning to control an object with two antagonistic muscles is similar in difficulty to controlling an object with one muscle. I would like to acknowledge the Human Neuromechanics Laboratory and my mentors, Dr. Daniel Ferris, Rylan Swearinger, and Nicole Stafford, for welcoming me into their lab and sharing their experience with me. I would also like to acknowledge the SURF program and specifically Mr. Mike Nazareth for organizing a unique summer experience. Getting to interact with students in different fields of engineering introduced me to new areas of research that I may not have been exposed to otherwise, and I'm looking forward to pursuing a PhD in biomedical engineering. I want to say thank you again to my mentors, the SURF program, and my fellow SURF members for making this a memorable summer.